Hello Lamai. Let's discuss the question number 2 under bulb systems, right? Okay, see what it says. Consider following system with two glass bulbs filled with A gas and B gas. Two bulbs are connected with a tube of negligible volume, right? That is what it says, right? See, so there are two bulbs, right? One is a large one and the other one is kind of a small one, right? So connected via a tube with negligible volume, right? So this is bulb X and this bulb Y, right? Then the bulb X is at 327 Celsius and the bulb Y is at 127 Celsius, no? Right? So you have the A gas and B gas inside them, right? What else they are saying? When the tap is closed, the pressure inside bulb X was 1 into 10 power 5 pascals. They are saying the pressure here is 1 into 10 power 5 pascals. And bulb Y contains 0.06 moles of B gas. So they are saying 0.06 moles of B gas. There. The volume of glass bulbs X and Y are 2 decimeter cubes and 1 decimeter cube. So here it is 2 decimeter cube and this one is with 1 decimeter cube, right? What else? Yeah, that's all. That's data. Then what they are asking, calculate the following when the tap is closed. Calculate the following when the tap is closed. Okay. Number of moles of A gas inside bulb X and pressure of bulb B. Right. Those are a few simple questions, right? The first thing is about number of moles of A gas inside bulb X. So we clearly see with the bulb X, you know about 3 parameters. You know about the temperature, you know about the pressure, and you know about the volume, right? Temperature, pressure, and volume known. So what they are asking is actually the number of moles. So PV equals nRT is kind of a 4 variable equation. P equals nRT is kind of a 4 variable equation. If you know about 3 variables, you can find out the missing 4th variable, right? So that is the idea here. So we can apply the P equals nRT to bulb X to come up with the number of moles of A gas inside bulb X, right? Okay, let's apply this stuff, right? So applying PV equals nRT to bulb X, right? So to bulb X, to bulb X. So the pressure there is actually 1 into power 5 pascals, 1 into 10 power 5 pascals. The volume is given as 2 decimeter cubes. We need to come up with the SI units. 2 into 10 to power minus 3 meter cubes is equal to N. The N, that is what we are looking for. Number of moles of A gas. R is 8.314 joules per Kelvin per mole. And T is 327 Celsius, that means 600 Kelvin. Right? So let's simplify the stuff. So we can take this one as 100 over 12, right? So it is going to be 10 power 5 pascals there, and 2 into 10 to power minus 3 is there, and Na is 100 over 12 and 600. Let's simplify. So here 2 of these things are there. So 10 to power 5 is there, 10 to power 4 is there, so those will cancel off with this one, right? So you have 2 and 2. 2 into 2 is 4. 4 into 1 is 2. No? So number of moles of A is going to be 4 into 10 to the power minus 2, that is 0.04, right? 4 into 10 to the power minus 2, no? Right? So that is the answer for the Roman number 1. Clear? No? right? Let's do here, right? Okay, let's do the Roman number 2. Pressure of B gas at bulb Y. Pressure of B gas at bulb Y. That is the second question they're asking. Pressure of B gas at bulb Y, right? Let's copy the pressure there, right? So we can apply the P equals nRT there, right? For the bulb Y, because again with the bulb Y we know about 3 variables. N is known, T is known, and V is known. P equals nRT is a 4 variable equation. When you know about 3 variables, you can use that thing to come up with the 4th missing piece, right? Okay, so N is known, T is known, and the V is known. So we can use these 3 data to come up with the unknown P, right? That is what we need to find out, right? So let's apply P equals nRT to bulb B, bulb B, right? To bulb B. So let's copy the values. The pressure, that is what we are looking at bulb B, and V is given as 1 decimeter cubes. So in SI units, 1 into the power minus 3 meter cubes. N is given as 0.06 moles. R is 8.314 joules per Kelvin per mole. T is what? 127 means it is 400 Kelvin. Right now? So let's simplify the stuff. You have 10 to the power minus 3 in this side equals 0.06 is there, and 100 over 12. We are substituting this thing as 100 over 12, and 400 is there, right? So let's simplify. So this is 3 here. So you have 100, so you can get rid of this thing as 6, right? Multiplying by 100, so it becomes 6, right? So 6 over 3 is just 2. So this sign P is there, right? Sorry for that, right? P is there. So when this comes to here, so you have 10 to the power 2 here, 10 to the power minus 3 here, altogether 10 to the power 5, right? So P is going to be, right, 2 into 10 to the power 5 pascals, right? No? 2 into 10 to the power 5 pascals. So that is the answer for Roman number 2, right? Things are clear, no? Right. So this value is written given as, we found that value as 0.04 moles, right? Right. Things are done up to here. The things are clear, right? Okay. So let's try to come up with the next one, right? Round number 3. Right. Then they are saying calculate the following when the tap is open. So after calculating this stuff, they are expecting us to calculate the things, some parameters after the tap is open. Then they have opened the tap, right? Let's discuss about that situation then, right? Okay. So I'll erase these things, right? So to come up with a new system when the tap is opened, right? Okay. So let's erase this one, right? So they have opened the tap, right? I'll write it here. This is before, and this is before. This is after opening the tap. Right? Let's come up with the picture again. You have this kind of a large bulb and a smaller bulb, the 2 bulbs, right? So now the tap is opened, right? This bulb X, this bulb Y, right? By opening a tap, right? Volumes won't change, right? Volumes won't change. These are rigid spheres, glass bulbs, So volumes won't be affected by opening a tap, right? So we can copy the same volumes. So 2 decimeter cubes and 1 decimeter cube, right? So they are not mentioning anything about the temperature change, right? They are mentioning nothing about the temperature change. So we can assume the temperature is also kept at same values, right? So temperature is going to be 327, right? At here. For this one, we can assume it as 127 because they haven't mentioned anything about the temperature change, right? If they have done so, they have mentioned that thing, right? Okay, right. What else? That is the things which are not going to change, right? So when opening the tap, what will happen? The A gas molecules will travel to the bulb Y and B gas molecules will travel to bulb X. That is the diffusion, the concept of diffusion, right? Okay, the things will travel from higher density to lower density. So you have more A molecules here, you don't have any A molecules there, so that A gas molecules will travel from bulb X to bulb Y, and B gas molecules you have much more here but nothing here, so B gas molecules will travel from bulb Y to bulb X, right? So that you get a homogeneous system ultimately, right? Homogeneous mixture ultimately, right? So ultimately you will have the A gas as well as B gas here. In this thing also you will have A gas as well as B gas, right? So it will be a homogeneous mixture, right? Throughout the whole system. Now the concentrations would be the same. That means the mole fractions would be the same, right? What about the total pressure in the stuff, right? So total pressure. If you think of the total pressure with both bulbs, that is going to be the same, right? Until the pressure become equal, the mixing stuff will occur, right? That is the idea here with the bulb systems. So total pressure will be the P total at both the bulbs, right? And with the bulb X and bulb Y, we can assume the pressure by the pressure by the gas A as PA and pressure by the gas B as PB, right? Those will be also equal, right? That is what happens until the pressures becomes equal, the stuff will mix, right? That is the idea with the bulb systems, right? Okay, so the things are done. So what will happen? So if you take right, the number of moles of total gas available here, number of moles of total gas available here, if you take it as x moles, number of moles of total gas available here as x moles, then the total moles of gas available here would be the n total minus x. The n total minus x. The total number of moles is the summation of these two, right? For both the gas, the total number is summation of these two. That means 0.4 plus 0.6. The total value is 0.1. That minus x moles will appear at the bulb Y. If x moles are appearing at the bulb X, the 0.1 minus x moles will appear at the bulb Y. Because this is kind of a closed system, right? So none of the gas molecules, right, moved out from the two bulbs, and none of the gas molecules were added to the right complete system. None of the gas molecules have been right released from the total system or added to the total system, right? So that the number of gas molecules at the beginning should be conserved at the end as well. So you have, if you are with x moles here, definitely this should carry the total minus x moles, right? Okay, the total is 0.04 plus 0.06, that is 0.1, right? Okay, so let's apply the stuff here. So the Roman number 1, what they're asking, amount of gas inside bulb X, amount of gas inside bulb X, right? That is Roman number 3, sorry, Roman number 3. So when solving these kind of questions, our major idea is the pressure inside the two bulbs are equal, right? So when it comes to pressure inside two bulbs are equal as P total, right? So we can write this stuff, right? So P of bulb A is equal to pressure of bulb B, right? Let's apply the values. Bulb A, for the bulb A, right, we can write it as the pressure PV is equal to nRT. If you subject the P is going to be equal to nRT over V, right? Let's apply these values here. So for the bulb A, it is going to be number of moles of inside the bulb A into R, and the temperature of the bulb A divided by the volume of the bulb A, VA, is equal to number of moles appearing at the bulb B, R, and the pressure of the temperature of the bulb B divided by the volume of the bulb B, right? So R will be cancelled off. Let's apply the values there. So number of moles at the bulb X, the two bulbs are not the A and B, no, two bulbs are X and Y. Label them properly. The two bulbs are X and Y. The two gases are the A and B, right? Two bulbs are X and Y, right? X and Y. Right now? Okay, let's apply the values, right? So for the bulb, right, for the bulb X, you are with X moles, right? You are with X moles. So take it as X moles. And T value for the bulb X is actually 327 Celsius. That means in Kelvin, it is 600 Kelvin divided by volume of bulb X, that is 2 decimeter cubes. So 2 into 10 to the power minus 3 meter cubes, that is equal to number of moles at the bulb Y, it is 0.1 minus 6, total minus 6, right? Into temperature is at 127, that is means 400 Kelvin divided by the volume. So volume, what is the volume? 1 decimeter cube. So 1 into 10 to the power minus 3 meter cubes, right? Sorry, meter cubes. Right. So let's simplify the stuff, right? These things will cancel off. These two things, right? Okay. So you can simplify this one as well. 4, 2, and 3. Right? So you'll come up with 3x is equal to, this goes to here, it becomes 4 then. 4 into 0.1 is 0.4 minus 4x, no? Right? So it becomes 7x is equal to 0.4. Then the x value is 0.4 divided by 7. So that is 0.057 is the number of moles there. Right? So this is the number of moles at the bulb X, amount of gas inside the bulb X and Y. So this is the number of moles at bulb X, right? Right? So what is the number of moles at bulb Y? That is 0.1 minus 6. 0.1 minus 6 becomes 0.0 43, no? This is number of moles at bulb Y. Right? No? Those are two answers for the Roman number 3. Number of moles at bulb X and bulb Y. Right? So we had found the numbers as 0.057 and 0.043. Okay, done. What else then they ask you? Total pressure of the system. Total pressure of the system. So to compute the total pressure, right? Now we know the number of moles appearing here. Now we know number of moles appearing here, right? Now we know the number of moles appearing here, right? This value, x value is known, that is 0.057, right? Now we know this value, x value, right? That is, right? Total number of moles 0.057. Total number of moles. As we know this value, can't we apply the P equals nRT to is total system? P equals nRT to total system, right? Then volume is known, temperature is known, moles is known. So to the bulb X, if you are to apply the P equals nRT, you can come up with the pressure of the bulb X. Pressure of the bulb X, that will be equal to the P total. That will be equal to P total, right? Pressure of bulb X as well as pressure of bulb Y will be equal to P total, right? The idea is clear. Same pressure, right? Same total pressure applies to the two bulbs, right? Okay, let's do the stuff, right? So Roman number 3. Sorry, Roman number 4. Applying PV equals nRT to bulb X, no? Right? So pressure, the total pressure of the bulb X, total pressure of the bulb X can be taken as, right, P total, right? This stuff, right? P total. So instead of total pressure of the bulb X, you can take the P total into B, the volume of bulb X, that is 2 decimeter cubes. So 2 into 10 to the power minus 3 meter cubes. Number of moles at the bulb X, number of moles at the bulb X is just calculated as 0.057 moles. R is 8.314 joule per Kelvin per mole. And T is what? That is 327 Celsius, means 600 Kelvin. 600 Kelvin. Right? That is clear. So you see the stuff now. Mole 600 Kelvin. Right? Okay. Let's simplify. Right? So this is going to be, you have the P total here. 2 into 10 to the power minus 3 is there. So 0.057 can be taken as 100 over 12. 600, no? Right? This will be cancel off. 2 here. Right? So this is 5.7. Right? 5.7. This 100, no? This becomes 5.7. Right? 5.7 divided by this 2 comes here, 4. 5.7 divided by 4. Divided by 4, no? This is going to be 1 point. Right? 1 is remaining. For the 17, it is 4. 1 is remaining. So for the 10, it's 2. 2 is remaining. 25, no? 1.425. So 1.425 into, right, 10 to the power 5, no? This comes here as 10 to the power 3, no? 10 to the power 5 we are doing that. So pressure P total is equal to, right, 1.425 into 10 to the power 5 pascals. Right now? So answer is clear. So that is the total pressure. That's the total pressure which will be applied on bulb X as well as bulb Y. In all the system, that is the total pressure, right? One same wall appearing. Only just one single wall for total system now. You don't have two walls like this, as the two things are not right. Separated by the tab, right? So as the tab is open, no separation of the walls. So one single wall appearing. So that one pressure should appear at both the bulbs, right? That is this value, total pressure, right now. So next question, partial pressures of A gas and B gas at this system. The partial pressures of A gas and B gas at this system. That is the next question, right? So I'll add them here. Partial pressures of two gases at this system, right? So for the calculate the partial pressures, if you know the P total, right, we can copy the partial pressures using Dalton's law, right? It says the partial pressure is equal to mole fraction into P total, mole fraction into P total. So then what is the mole fraction? What is the mole fraction? In considering the total system, right? In considering total system, right? The total stuff, right? Inside this total system, right? You are with 0.4 moles of A gas, this total system, right? Number of moles of A is 0.04 moles, and number of moles of B, I write it here. So the total system, you have 0.04 moles of A, and B, you have 0.06 moles of B. Those are the values of A and B at the total system. So the mole fraction is total number of moles, your number of moles divided by the total number of moles. Your number of moles divided by the total number of moles will give you the mole fraction. So at the total system, the mole fraction of A is 0.04 divided by the total number, that is 0.1. 0.04 divided by the 0.1 is the mole fraction of A at the total system. That will be equal at here as well as here. So this is a homogeneous system. This is a homogeneous system, right? As this is a homogeneous system, right? Total number of moles, the mole fraction is the same at any point inside the system. At any considering point inside the system, the mole fraction will be the same as is a homogeneous system, right? So that the mole fraction at the bulb A, bulb X, or at the bulb Y, anywhere, is going to be equal to the mole fraction of the total system, right? Okay, so that is what we are applying here, right? So let's complete those, right? So this is Roman number 5, right? Mole fractions are equal at two bulbs, right? Mole fraction, we say mole fractions are equal to two bulbs. A system is homogeneous. A system is homogeneous, right? So that means if you need the idea, XA at bulb by, sorry, bulb X is equal to XA at bulb by, actually it is equal to mole fraction of total system. So one can say XB at bulb X is equal to XB at bulb Y is equal to XB at total system. Right? This is the idea there. So we can use this thing to come up with the mole fractions. So first come up with the, sorry, you can use this thing to come up with the mole fractions, ultimately to come up with the partial pressures. So PA is actually XAP total, right? So the XA is the number of moles of A, that is 0.04, divided by total number of moles, that is 0.04 plus 0.06, that is 0.1, into P total, that is 1.425 into the power 5. So the value is going to be like just multiplying these things, right? So it is going to be 0.4 multiplying by 1.425. It's going to be 0.57, no? And it's going to be 0.57 into 10 to the power 5 pascals. This is the partial pressure of A at here, as well as at the total system. That is this idea, right? So what about the partial pressure of B? So PB can be written as XB into P total. XB is the number of moles here, 0.06, divided by the total moles, that is 0.1, into P total, that is 1.425 into 10 to the power 5 pascals. So that value is actually this thing minus this, right? You can compute as that as well. So this is going to be 0.06, no, 0.6 into 1.425. That will be given as 0.855. Pascals. And those are the two answers for the Roman number 5. Right now, things are clear. Right. So answer is Roman number 3, right? And here the values for the Roman number 4. Okay. Just complete the stuff, Lama. Let's discuss the question number 3 under the bulb systems. See, so here the theory is about the bulb systems as well as the theory is about the reaction table will be discussed, right? A good question. Let's go to the question here. What it says, first of all, the following gas bulbs A and B are filled with helium, N2 and O2 gases according to the following diagram. So some diagram is given, right? Let's go to the stuff, right? So this is the diagram, right? So you have a small bulb and a large bulb. No, yeah, the bulb is small. A large bulb. Okay, and connected with a valve. So connected with a tube with a negligible volume, and valve is closed. at the beginning, right? So you have the bulb A here and bulb B here at 127 Celsius with the bulb A and 4.157 decimillimeters the volume. This thing is 227 Celsius and 16.628 decimeter cubes, right now. So tap is closed and you have helium gas here, 0.1 moles, and N2 gas here. So I can't put a different color, some N2 gas here, and moles are not given, right? They may ask you to find that moles, right? Some O2 gas here, so I can't put a different color, right? Some O2 gas here, right? So that is how the bulbs look like. And pressure inside the bulb A when tap was closed is given, right? Pressure inside the bulb A is given as 2.4 into 10 to the power 5 pascals, no? That value is given, right? Yeah, and they are asking some question, no? Right. So Roman number 1, what they are asking? Total number of gas molecules. Total number of gas molecules. That is what they are asking. So when it comes to bulb A, right? You know the pressure, right? You know the volume, you know the temperature. What they are asking is the total number of gas moles. What they are asking is the in total. That is what they are asking as a question. The in total, right? So to see, they are asking the in total. Huh? They are asking the in total, right? So can't be fine. So you know the pressure, volume, and the temperature. 3 variables are known, so that we need to come up with the 4th variable, the missing piece, right? So we can apply the P cos n RT, which is a 4 variable equation, right? So let's come up with that. Applying P cos n RT to bulb A to come up with the total number of moles at the bulb A, right? Apply PV cos n RT to bulb A, right? So the P value is given as 2.4 into the power 5 pascals. B is given as 4.157 to power minus 3 meter cubes, right? N, that is what we need to find. R is 8.314 joules per Kelvin mole, and T is given as 127. That means let's take it as 300. Sorry, 400. 127 means 400. Right. Let's simplify this stuff. So basically, these will cancel off. 4.157 is the half the value of this thing. Right? So what else? So you have 2 zeros. Those two will come here as -2. So -2 and -3 is -5. So 10 to the power 5 is there. Those things will cancel off. Right? So you have 2 into 4 is 6. This is into, right? It's just like this now. So 2 into 4 is 8. 2 into 4 is 8. And that will cancel off with this thing, right? 1 of 8s, and here you have 0.3. So total number of moles. So total number of moles is actually 0.3. So NT is 0.3 moles. Right now? So number of moles of N2 gas. Number of moles of N2 gas. Right? Total number of moles at the bulb B. Because the bulb B, that is where the N2 gas is at, right? Bulb B, so where the N2 gas is at, sorry, right? So the in total is equal to the two gases there, moles of N2 plus moles of helium, right? So N total value is given as 0.3 moles. It is equal to the moles of N2 plus the helium value. The helium value is given as 0.1. Right? This will give you the moles of N2. Is 0.2 moles. That is clear? Right. That is how we are supposed to come up with the N2 moles here, right? N2 moles. So this value was found, right? The N2's value was found now as 0.2 moles. Right. Okay. Third question. If the amount of O2 in bulb B when tap was closed was 0.3 moles, they are saying this value is 0.3. The Roman number 3, they are saying this value is 0.3. Then they're asking is find the pressure inside the bulb B. Find the pressure inside the bulb B. So now the question is not hard, right? So what they are asking the pressure. What they are asking is the pressure. They are asking is the pressure inside the bulb B. So again, we can apply the Peterson-Nardi as it's a 4-variable equation. You know about 3 variables here. T is known, B is known, and the N is known. So you can use the Peterson-Nardi to come up with the missing 4th variable, which is P, right? So let's use the Peterson-Nardi to bulb B, right? So from number 2, right? For bulb B, apply the Peterson-Nardi. So applying P Peterson-Nardi to bulb B, right? To bulb B, right? So the P, that is what we are looking for. P is what we are looking for. B is given as 16.628 into the power minus 3, as we need to come up with the meter cubes, these units. N is given as 0.3 moles. R is 8.314 joules per Kelvin per mole. T, the 227 means 500 Kelvin. So we need to add 273 to the Celsius value to come up with the Kelvin, right? So we need to apply the Kelvin values here, as less units are needed in applying the P equals NRT, right? Right. So let's simplify the stuff, right? So 8.314 is the half value of this thing, right? So you have 2 here, 1 here, right? What happens? So you can count like this. P is there. You have 0.3 and 5, and I'm going to bring this thing to here. So it is 10 to minus 3 becomes 10 to power 3, and some 2 is there, so power 5, right? And 2 will be here, like that. Okay, so the value is going to be, right? The value is going to be, so this is 1.5 divided by 2. So 0.75 no? into 10 to power 5 pascals. One can say it as 7.5 into 10 to power 4. 7.5 into 10 to power 4 pascals. So 0.75 into 10 to power 5 pascals, right? That is clear? Right? Okay, that is for the Roman number. Sorry, Roman number 3. No? This is Roman number 3, right? Roman number 3. 2 we had calculated. Right. So the pressure here was also calculated as 0.75 into 10 to power 5. Things are done. Right. Now they are opening the tap. Right. The tap was opened after raising the temperature up to 327 Celsius. Into gas and auto gas reacted partially according to the following equation, right? So okay. So they are opening tap, right? I'll erase this stuff, right? Is that clear? So I need to copy the next picture there, right? Okay. So they are opening the tap, right? Right. Okay. Right. This is the before picture. Now after opening the tap. after opening tab, right? Right. So how it looks like. So two vessels are there, right? Two vessels are there. Sorry, two vessels are there. The volumes won't change, right? These are jet vessels. By opening a tap, by changing a temperature, these things won't change the volumes, right? Volumes won't change. These are rigid vessels, right? Glass bulbs, right? So, right. So you have the bulb A, bulb B, right? So volumes won't change. So those stands at the initial values. So 16.628. So what they have done is actually they have changed the temperature, right? They have changed the temperature to a constant value for the both the bulbs, right? So now the with the both the bulbs, the temperature is going to be 327 Celsius, right? 327 Celsius, right? So with both the bulbs, they come up with 327 Celsius. They have mentioned that they have changed the temperature, right? They are saying when the tap was opened, after reducing the temperature up to 327 Celsius. Both are with the same 327 Celsius now, right? So this whole system behaves as a one now. This whole system behaves as a one. No need to think of two bulbs, right? This whole system behaves as a one, right? So both are the 327 Celsius now. So you can take the whole system. You can consider the whole system now because there's one compartment here, right? You can take the whole, and volume can be taken as, right, the summation of these two, right? 4.157 plus 16.628. The summation. So actually, if you are to simplify this stuff, it is like, right, 2 times of 4 times of 4.157 is there. So that is 5 times of 4.157. Right? You can take the right whole system as a one compartment, right? Both are the same temperature, means no need to apply the stuff separately. So one compartment is appearing, right? So just one compartment is appearing, and N2 gas and O2 gas will react there. So basically, O2 will travel to here, N2 will travel to here. The things will mix, and they will react, right? They will react, right? So the at the core system, so you can apply now the things, right? So now system is like this, right? I'll bring the things here. So this is the initial point. Our system, this is the initial point, right? At the core system, you have N2 gas 0.2 moles and some O2 gas, right? 0.3 moles at the core system, right? It's just the one system, right? Whole thing. So this is before reaction. This is before reaction. This is the initial state. This is the initial state. Before reaction, right? Then we can think of a final state as well after the reaction. So we have to compare those two stuff, right? Okay. So let's come up with the reaction table, right? Let's come up with the reaction table, right? Okay. We can come up with the reaction table. So some reaction is happening, right? So the reaction is this. N2 gas is reacting with 2O42 gas to give you 2 of NO2 gas, right? It's initial moles, change moles, and the equilibrium moles. right? So let's apply the values here. At the start, you have 0.2 moles of N2, right? 0.3 moles of O2 at the start, and you had nothing as N2 at the beginning of the reaction, at this initial state, right? What else they are providing? After reaction, total pressure of the system is reached to 1.2 into the power 5 pascals, right? So at the end, some pressure value is given. At the end, some pressure value is given, right? At the end, they are given some pressure value, right? The total pressure as 1.2 into the power 5 pascals, right? With the use of the pressure value at the end, at this end situation, right? They are providing us the pressure value, right? At the end system, they are giving us the total pressure as 1.2 into the power 5. Right? That value is given, no? Given data at the end of the reaction, right? So the questions they are asking is total number of moles inside the system, number of moles separately, and the stuff, right? Okay. So to calculate the total number of moles at the end of the process, how to calculate this stuff? So basically, right, total number of moles needed to be calculated, right? So how come? So if you have to apply the P equals nRT to calculate the total number of moles, you should know the other three variables: the pressure at the end, volume at the end, and the temperature. Right? P equals nRT is a 4-variable equation. So if you know about the other three variables, then you can calculate the fourth missing piece, right? Okay. So they are asking is to calculate the, right? This is Roman number 4, no? What they are asking is to calculate the number of moles. What they are asking is to calculate the number of moles, total number of moles. So at the end of system, you know the pressure, right? You know the temperature. The temperature is at 327. This reaction table is constructed to 327, right? At the end, you know the temperature, you know the pressure, you know the volume as well, rigid bulbs. The same system will appear at the end, right? The bulbs won't change, volume is just solid. So if you know to draw the stuff, I'll draw it here. If you know to get some clear idea, right? It's the initial system. After opening tab, right? This will convert to the equilibrium system, right? How it looks like. This also with the same two bulbs, right? Bulb A and bulb B. Those are with the same volumes, right? So those are with the same volumes, 4.157 decimeter cube, 16.628 decimeter cubes, and inside the 327, right? Inside 327. This is the final system, how it looks like after the reaction. System after reaction. So what they are asking is the, right, total number of moles here. Total number of moles here. That is what they are asking, right? In total here. At the final system, right? This initial system is final system, right? Okay. So in this case, we know the P total. They have provided the P total as 1.2 into 10 to the power 5 pascals. At the equilibrium, they are providing the P total, so that we know the P total, we know the temperature, and we know the volume, the same volume, right? And now we can come up with the total number of moles. So applying P total V is equal to N total RV, right? To system at equilibrium. System at equilibrium, right? So total pressure is actually 1.2 into the power 5 pascals. V volume is the total volume here, right? Same volume, right? It can be written as 5 into 4.157. No? What is the in total? What is the in total? Right? What is in total? That is what we are looking at, right? This is what we are looking at in total. And this is 8.314 joule per Kelvin per mole multiplied by temperature is 327 means 600 Kelvin. Right? It's simple stuff, right? So you can read it of this thing with two of these. Right, 10 to the power minus 2, this 10 to the power 2 comes here as 10 to the power minus 2, and this 5 will cancel off with the minus 5 there. So you have 12 here, 6 into 2 is 12 here, so this is 12, 0.1, right? So N2 is going to be 0.1 into 5, 0.5. In total is going to be 0.5 moles, right now? In total is 0.5 moles. No worries, no? Right, that is the answer of the Roman number 4. What about Roman number 5? Number of moles of N2 and O2 and NO2 separately, right? So now we know the in total. Now we know the in total as 0.5, right? Now they are asking these values. How to come up with these values? Let's complete the reaction table. To convert the initial values to the equilibrium values or the end values, definitely we have to come through a reaction table, right? We need to complete the reaction table to come up with these values. But unfortunately, now we don't have a column with two values filled. We don't have a column with two values filled, right? So you need to come up with the unknown. Just take it as x. Just take that unknown x, right? So you can take the reacted amount as x. So if it is x, 1 to 2 ratio, no? So it becomes minus 2x, 1 to 2 ratio, right? This is also 1 to 2 ratio, so plus 2x producing, right? So 0.2 minus 6 is 0.2 minus 6, the end value is 0.3 minus 2x is just 2x, right? So if you are to add these values, add all of these values, the in total will be what? In total will be what? So I'll take the things to here, no? Right? You take these values. Your in total is equal to 0.2, 0.5. Sorry, we forgot about the helium, no? We forgot about helium. Helium was also there, right? Sorry about that. We have to bring that thing as well. Helium gas was also there, 0.1 moles. At the beginning it was 0.1. Not involved with the reaction. So at the end also there should be 0.1. Don't forget that thing. It's a non-reactive gas, right? So the total number is going to be 0.2, 0.3 and 0.1 is 0.6 altogether. Minus these two will cancel off, minus 6, no? So reaction table says the in total is 0.6 minus 6. The P-cosine says it's 0.5. So these two are equal, right? So This is 0.6 minus 6. So you can copy x so that x is equal to 0.1 moles. X is equal to 0.1 moles, right? So now we can copy the values at the equilibrium, right? So this is Roman number 5. So I put the values there. So we have some space now. Number 5. So number of moles of N2 at the equilibrium is just 0.2 minus x, it is 0.1. So it is going to be just 0.1 moles. So number of moles of O2 gas at the equilibrium, 0.3 minus 2x. 0.3 minus 2x means 2 into 0.1 is 0.2. For the next plan, right? For the NO2, so you won't see this stuff, no? So I'll write it here. For the moles of NO2, that is just 2x, no? 2x is equal to 0.12 is 0.2. Right? 0.2 moles. Right. Okay. That is the Roman number 5. Final thing, the partial pressures of the stuff, right? So partial pressures of the stuff here. So at the end, now you are with some N2 gas, that is 0.1 moles. Then you have it some O2 gas, which is 0.1 moles as well. And so produce NO2 is there, 0.2 moles. And don't forget the helium. Helium is also there, which is 0.1 mole. So that is how the end flask looks like. Flask at the end, or the system at the end looks like. These 4 guys are appearing, right? Right. So let's copy the partial pressures of N2, O2 and NO2, right? So Roman number 6. So partial pressure of N2 is equal to mole fraction of N2 into P total. The mole fraction is total number of moles is actually given as 0.5. This value. So total number of moles is 0.5. Total number of moles is 0.5. Number of moles of N2 is 0.1 into P total. P total value is total pressure 1.2 into the power 5. Right? So that value is equal to, right, is just 0.2 divided by, 1.2 divided by 5, right? So this 1.2 divided by 5, 0.24 or 5 viscous, right? So if you are regarding the partial pressure of O2 gas, it is same as the partial pressure for N2 gas, right? Because the mole fraction is same number of moles appearing with the O2 as well as N2. The mole fraction is still 0.1 into divided by 0.5. P total is same, right? So the same number will appear as the partial pressure of O2 as well. Right now, then for the partial pressure of NO2, the partial pressure of NO2. Again, the mole fraction is going to be, its number of moles is 0.2, total number of moles is 0.5 into P total is 1.2 into 10 to the power 5 pascals. Right now, so that value will be equal to twice of this value, right? Twice of this value. That is going to be 0.48. To the power 5 pascals. Right now. So, want to see? I'll write it here. It is 0.48 into power 5 pascals. Right now, that is the answer for the question number 3. Right? Things are clear. So you can complete the stuff, right? That is all about the question number 3. Right? So we'll end our discussion with this thing, right? So you can complete the notes, right? So just complete these questions. Goodbye then.